Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz. I just want to say thanks very much for joining us today as we look at our topic of how to test power tools, the calibration, and its reliability. And so if you do have any type of questions or comments, you can go ahead and put those in the chat and we'll have a time to answer those questions at the end of the presentation after the demonstration. But if you've had the opportunity to see any of our other webinars, one thing that we typically always highlight is going to be the torque failure possibilities and how that can affect what happens with that part as it moves down the line if there is a torque failure. And you can have a few cent fastener fail, and that can really cause a lot of damage throughout the process. And so if we can help to mitigate and monitor those types of fastening errors, such as under torquing or over torquing, both of those do have the same type of failure risk at when the entire assembly can be disabled or cause, again, a lot of rework and things like that. So if we can manage and have good foundations and practices in our process to help mitigate those types of failures, it can really help to move us and move the process into a really good state. And so today, when we're looking at the value of measuring torque, there are a number of positives that we can do with that scenario. And so obviously we want to be able to evaluate the quality of our process, evaluate the quality of the performance of the tool that we may be testing. But this gives us the ability to not only see what is going on with a particular joint or a particular assembly process, it can really shine a light on what is actually going on. It can help us to recognize what may be a root cause within the assembly process. And if there is a fastening issue, oftentimes the first thing that is looked at, and probably rightly so, is going to be the performance of the tool. But the tool may not always be the issue. We will talk about other things that can make up the actual information that we would be receiving, but the tool itself may not always be the root cause of poor fastening. We'll also look at the value for validating and looking at, again, diagnosing any type of process failure or process assembly instructions or things like that. If we have the ability to measure what is happening, again, with the assembly, we can take a better look at that. We can ensure that the tool that we're testing is being repeatable and it's being accurate. And those are two separate things, and we'll touch on that as well. The other nice thing about measuring torque, especially with a calibrated device, is the ability for that tool then to have traceability to a higher standard within that testing process. And with that, you also have, again, documentation that you can use to help with maybe ISO 9001 requirements and certain other internal documentation regarding how your tools are performing in certain applications. And by doing that with measuring the actual tool in the assembly process, this can give us really good documentation for that use. And so when we're talking about power tools, there are a couple of things that we need to understand about how we're going to be measuring that particular torque of the tool. And there's two basic states of measuring torque. And so we have a static torque And then we also have a dynamic torque. And so a static torque is measuring a fastener that has no motion to it. It's already been fastened, maybe in an auditing process where we might do either a breakaway style test or a first movement test or a line test where we mark the part and the line on the fastener, and we move those or we break that away, and then we bring those lines back together and measure what that value is. Those would be examples of a static torque. So we're not really measuring anything that has any dynamic ability to it. So the dynamic torque is going to be that where we see motion, a constant motion of the fastening process, and then we measure what that is. And again, this is done through the use of different sensors to measure static torque and also dynamic torque as well. And so the power tool itself does have some really big advantages to the assembly process. It gives us the ability to use speed and RPM during that rundown. It gives us the ability to add automation to our fastening process. And it also helps us to be a little bit more productive during the assembly versus like a hand tool or such. But there are a few things that need to be taken into consideration when we look at a specific application or a specific joint. And that's going to be the type of materials that are being used. Also, if there's going to be any type of lubricant that's going to be used or any type of gaskets. These types of materials and changes to a specific joint can make the torque output vary quite a bit. Obviously, when we talk about lubrication, if there is in a application a fastener that is run down without lubrication, and then we go ahead and we add some lubrication by accident or on purpose, that is going to change the amount of clamp force that tool is generating. Now, it may be generating the same amount of torque, but because we've reduced the amount of friction that happens during the actual rundown, that is now causing the fastener to stretch more than it was designed for a specific application. And the clamp load then is going to be increased, putting extra stress on that fastener, which may lead to the yield point of that fastener, to permanent deformation, and any type of shock or vibration is going to cause that fastener to break or fail. And so again, the types of materials that are being used with that, especially if you move to some type of from maybe a metal washer to a plastic washer, all of these types of components can play a part in the actual torque output that the tool would be generating. And so for us to be able to test that, we would use what would be a rotary sensor. And so what is a rotary sensor? Well, it is basically a shaft that has a strain gauge on it. In this first scenario, this is more of a reaction style transducer, but we have a strain gauge there, electrified circuit. And as there is torsion on the stock, we get different resistance readings throughout the or the output from the electrified circuit. Now, in the rotary sensor, we use slip rings that are over the strain gauge, and we can measure the difference between the different slip rings, and this will then provide us with the torque that is being generated with the power tool. And so this allows us to be able to put the rotary sensor basically in between our tool and our part, and then we can measure actually on our application what the actual torque is. And so with the rotary sensor, we can use electric clutch tools. We could also use a pneumatic clutch or pulse tools with that. And those can have different configurations. It could be a right angle tool, it could be a pistol grip tool, but the sensor works in conjunction with a torque analyzer, again, allowing us to be able to test our tool on our part. And so this differs slightly from if this tool is sent out for calibration, because the calibration, whether it's in-house or if it's going to be sent out to another lab, they are going to be testing that tool on a joint simulator. And so that simulator may not have the same characteristics as the actual joint that's being used. So if we have the ability to use a rotary sensor, the big advantage is that we can use it actually on our part, and we can tell the amount of torque that we are getting on our application, not just on the joint simulator. And so this allows us to use what we like to call torque verification. And this really helps to eliminate or reduce some of those risks that we talked about at the beginning of some of the torque failures that we might see. But the big component to that is we can actually see how our tool is performing over time if we have a system set in place with different frequencies of testing our tools in between the actual calibration dates of that tool. And so we can see and we can check to make sure that the tool is still within its calibrated limits through the torque verification process. And again, this would be having the ability to go to the line, test your tool on a periodic basis, and make sure that it still is within the calibrated limits. Because the last thing that anyone wants is to have a tool sent out for calibration, have that tool come back, and with a certification that was saying that the tool was found out of its specification. And now this begins the process of trying to figure out at what point did the tool go out, if it is a 6-month or 12-month calibration, what parts were affected by that tool, is there a need for rework, is there a need to do any type of recall or things like that. So if we have that ability to monitor the tools while they are still within their calibration period, and we know that they're not out of the calibration parameters, then obviously we can be confident that when we get those tools back from their recertifications, that they are still within their calibrated limits. So again, the torque verification process just helps to reduce any exposure to those types of risks. So there are other facets of the manufacturing process that we can use the testing for. We can use it prior to the assembly for setting up the tool. We can use it for any type of R&D type of capability studies that we might want to do. So it'd be kind of prior to the assembly. During the assembly, we just talked about the torque verification and the torque validation process. And then we can also use them again for after the assembly if we want to do some torque auditing or recalibration of those particular tools. So these are different areas which we can use the sensor as well. So that's going to lead us to our poll question today. And so let's go ahead and we'll launch that poll. And the question is, when you test your tools or do verification when do you do that power tool calibration certification? So we'll let you go ahead and answer those questions, and then we'll be right back with you here in just a second. All right. So we still got a few answers coming in. It looks like the main answer here, or the winner, is once the tool's annual calibration is in effect, followed by before the assembly process. Now, the rotary sensor, we can use at, again, different frequencies of testing, but it's a good idea to understand what different sensors are available for different types of applications. There are two main styles of rotary sensors. The first one is going to be a brush system, which is very similar to the animation that we looked at. And then we also have a brushless rotary sensor as well. And the brushless sensors are used primarily for situations where the customer may want to have the sensor taking readings during the actual assembly process, and the sensor is going to remain in the assembly line where it's constantly grabbing information during the use of that. So that's a good example of using a brushless type of sensor. We'd also recommend using a brushless sensor for the use of any type of pulse tool that is going to be used. This helps because of the way that the clutch mechanism works in a hydraulic pulse tool. You can get a scenario where you may see some brush bounce with a brush type of sensor. So using the brushless sensor helps to give you a better accuracy as far as the readings are concerned if you are using a pulse tool. Now, you would never ever want to use a impact tool with a brush or brushless rotary sensor, or any torque sensor for that matter, but that's something to keep in mind with the rotary sensors. There's also one additional style of sensor, and this sensor not only will be able to capture the torque, but it also can provide an angle signal. So as rotation is happening, you can see what that torque value is based off of a certain amount of turn or angle, and you can grab that information from the sensor. So those are the different styles of rotary sensor, and again, these would all be paired with a torque analyzer. These systems are a calibrated item, whether it be the Z540 or an ISO 17025 certificate. So this is a calibrated piece of equipment that would need to be calibrated on a periodic basis as well. Now, here's an example of a on-site customer that would be using this in a scenario where they're constantly monitoring the values of this particular tool. And in this scenario, it is actually a pulse tool that is being used. And so we are using the brushless sensor in conjunction with our PTT torque analyzer. But this kind of gives you an idea of what that looks like within the assembly process. And we'll do the same thing here within our demonstration, just to show you how the tool works, or the sensor works with the use of a power tool. So let's go ahead and we can jump into our demo here. And so what I have is one of our rotary sensors. This has a capacity of 5 to 50 inch-pounds. And we'll be testing this tool that has a torque output of around 9.3 or so inch-pounds. And so with the use of the torque analyzer, we have the ability to save the readings. So I'll use our tool test function where I've got this set for a low limit and a high limit, and we'll go ahead and start the test, and it will capture 5 readings for us, and then it saves that information into the reading. And so right now we don't have any readings saved. I do have the tool set to automatically reverse after the torque, so we can go ahead and do the next one here fairly quickly. So now we've taken 1 reading and 2 readings, and the analyzer itself is set to automatically clear after 2 seconds. And then once we get to our 5th reading, it will then go ahead and let us know by resetting that we have achieved those torque readings. And so it makes it very, very easy to be able to, again, go out and be able to put the tool actually on or the sensor onto your tool. You can put it, again, the bit goes in one side, and you go ahead and just sandwich it in between. Go ahead and take your torque readings and then make sure that you are within your torque specifications. Now, within the torque test or the tool test that we did, we do have the ability to have a green and red light notification. So that can be set up for that particular tool, and the operator or the tester, just person, just needs to look at the light to make sure that it's within the specs. And if it is, then they continue to move on. If they get a reading that's outside of that, then they can flag that tool to have that either looked at or recalibrated. So everything else is good to go here. And that's going to go ahead and wrap us up here. And so we'll go ahead and move to our questions and answers right now. And so Casey will be compiling the questions. So Casey, do we have any questions?
So I'll read them for you from our web chat first, and then move into anything else that we have. So the first question we have is it safe to use pulse tools on rotary transducers?
Yes, it certainly is safe to use pulse tools. Again, you don't want to use an impact tool, but a pulse tool can be used with a rotary sensor. One thing that you may need to adjust is going to be the frequency or the hertz that that sensor will be capturing at. Because of the nature of the pulse tool, where it is basically it is pulsing, and so you get some really deep valleys in throughout the signal line, and so that can produce some inconsistencies. So if we increase that filter setting up to say it could be up to 1500 or 3000 hertz, that can help to give us a little bit more clarity when using the pulse tool with a rotary sensor on the torque analyzer. But typically with clutch type of tools, or either if you're going to be using a hand tool, we can leave that at 500 hertz for the filter setting.
All right. The next question that we have is, can a rotary sensor be used to verify clicker wrenches?
You certainly could do that as well. Yeah, anything that you put in between the tool and the part, you could use that for a click wrench, and that will show you the output that wrench is producing. Now we do have a setting or a mode within the torque analyzer called our first peak mode. And what this does is it will actually capture where the wrench clicks. It will also show you if there was any additional over torque from the operator not stopping once the wrench clicks, because the click in the click style wrench is just a signal to say stop pulling. If the operator does not stop pulling or pulls too fast or double clicks, they are adding additional torque than where the wrench actually clicks. And so If you do use the analyzer in a peak mode, which is going to measure the highest peak torque, you may see some really erratic readings. And so if you want to be able to see where the wrench clicks and then also where the wrench stopped, you could use a first peak mode type on the analyzer. So
Okay, and you may have just answered this, Dave, but I'm not 100% sure. So is there a standard filter setting for click tools? And if so, what is that? And then what about for battery or power tools?
yeah, so standard clutch tools and hand tools, you can be at 500 hertz for your filter setting. Again, you would only really need to change the filter setting if you're going to be testing pulse tools. And again, you'd have to do a little bit of testing to see what filter setting might be best, but somewhere at 1500 to 3000 hertz for the pulse tool.
Okay, so I think that is the end of the questions there. There's another one on here that says, what setting stages do you have within your equipment? Do you think that was covered by the last section?
I believe so.
All right, perfect. So that is all of the questions that we have for today. If you guys have any additional questions or if you need a more in-depth response to any of those, feel free to shoot a message to myself or to Dave. I'm going to put my email actually right into the chat box right now. I know that we have an email address listed for Chris Morris on the webinar invitation right now. I will be updating that to mine as Chris is on vacation. All right. Thank you guys for attending today, and we will see you guys next month.
All right. Have a good day.